Today we will discuss some examples uh, of homotopy between maps and some results related to homotopy of maps. First example, consider x equal to y equal to r n uh, x prime this and f naught and f1 uh, uh, from Rn to Rn is defined by f naught x equal to x and f1 x equal to 0. Basically, f naught is identity map on Rn. This is for every x in Rn. Then define capital F from Rn cross I to Rn by f x t equal to 1 minus t x, right? So you can verify that uh, uh, this capital F is a continuous function, that is a map from here to Rn, because you know that you can consider two maps. So one takes xt to 1 minus t, and then another takes xt to x. So this is a this is a map from Rn cross I to R, and this is continuous map. And this is a projection map, so this also is continuous map. And here you have multiplied these two, right? So this is going to be continuous. So in your topology course, you might have studied that this kind of thing. So this is continuous, and f is clearly continuous, and fx0 is what? When you put a t equal to 0, you have fx0 equal to x, right? That is nothing but f naught. So this is f naught x, and fx1 equal to f1 x 0, right? Because when you put t equal to 1, this is 0, and hence this you are getting 0. Thus, f is a homotopy from f naught to f1 relative to this. Now, let us see how this homotopy works, right? How this homotopy works. Let us see. So basically, you have, let us consider the case when n equal to 2, right? So, what does it do? Uh, so basically, given any point x, uh, what is this 1 minus t x? This is the when t varies between uh, 0 and 1, this 1 minus t x is represents the line segment joining x and 0 origin, right? Uh, so when t equal to 0, uh, your you have x goes to x, right? When t equal to half, right? You see 1 minus half is half, so uh, x goes to half x, somewhere here, x half x. And so, similarly, if you consider this uh, right, so this whole disk, when t equal to half, this whole disk is mapped to this smaller disk, right? This one. Uh, so basically, uh, 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 when you go from 0 to 1, this shrinking means maps are means consecutive maps are getting shrinked, right? Uh, right, their ranges are getting shrinked. Initially, when t equal to 0, you have identity map, so right, so x goes to x for every x in uh, Rn. Uh, but when you increase t from right, then uh, what means the maps are ranges of maps are getting shrinked more and more, right? So and in the end, when t equal to 1, everything collapses to 0. Everything goes to 0, right? So let us see next example. Uh, Here I can take x equal to y. Consider x equal to y equal to I, and uh, x prime equal to 0, and f naught f1 uh, from I I, given by 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 25 26 27 28 29 30 31 32 33 34 35 36 37 38 39 40 41 42 43 44 45 46 47 48 49 50 51 52 53 54 55 56 57 58 59 60 61 62 63 64 65 66 67 68 69 70 71 72 73 74 75 76 77 78 79 80 81 82 83 84 85 86 87 88 89 90 91 92 93 94 95 96 97 98 99 100 101 102 103 104 105 106 107 108 109 110 111 112 113 114 115 116 117 118 119 120 121 122 123 124 125 126 127 128 129 130 131 132 133 134 135 136 137 138 139 140 141 142 143 144 145 146 147 148 149 150 151 152 153 154 155 156 157 158 159 In the same way, f naught t equal to s, f naught s equal to s, and f1 s equal to 0 for every s belonging to I. Now define capital F from I cross I by f st equal to 1 minus t to s, right? So clearly this f is uh, continuous function, uh, and f s0 equal to this is s equal to f0s, and f s1 equal to 0 equal to f1 s for every s in I. So basically capital F is a homotopy, hence capital F. Of course, this uh, uh, capital F over if you consider this, you need to write this F S, sorry, F0 uh, t equal to 0 for every t in I, right? It means that hence uh, F is a homotopy from F naught to F1 relative to 0. So let us see what is happening here. So if you consider this interval 0, 1, right? 0, 1. So F, what does F naught do? It sends, it is identity, right? So it sends X to X for every point X here in this. And when your uh, this t is half, what does it do? So this s goes to half s, right? For example, 1 goes to half, right? And maybe if you consider right, so everything, this whole interval is shrink to this one. For t equal to uh, maybe 1 upon 3, what happens? Uh, we'll have something like this. So whole interval is shrink to this one, right? This whole interval is mapped to this one. So initially your f naught was mapping this to this itself. Then next, if you consider uh, uh, this one uh, f s 1 upon 4, right? Then so if you consider f s 1 upon 4, then what will happen? So this 1 minus 1 upon 4, that is 3 upon 4. So 1 goes to 3 upon 4. So something like here. And correspondingly other points also are getting right. So this whole interval is mapped to this one. Now if you consider yes, t equal to half, then whole interval is mapped to this one. When you consider t equal to 1 upon 3, then it is 2 upon 3, right? Uh, uh, so basically, uh, when t equal to 1 upon 3, it will be mapped somewhere here maybe, right? And when t equal to 2 upon 3, whole interval is mapped to this one. So if you keep on decreasing, means increasing the value of t, this um, the ranges of consecutive maps, right? So if we can write fs t equal to fts, right? So when t increases, right? When t equal to 0, its range is whole interval 0, 1. When t is 1, 2, and so on, right? When t is, sorry, when t is 1 upon 4, then half, then 3 upon 4, something like that, ranges are getting synced, right? So first for 3 upon 4 range is this much, then for half range is this much, then for uh, 3 upon 4 range will be, if it is 1 upon 4, range will be this much, and so on. For maybe, uh, yeah, so I hope that it is clear now. Uh, So basically what these maps are doing, their initially range was this, then if you consider the higher values of t, then ranges are getting same, right? So basically the mm, map is uh, getting deformed, right? So there is a this map, initial map was f naught, and slowly you are continuously deforming f naught to get f1. That is the idea, right? So this map is this is a continuous deformation of the map of the map f naught. Next example 3. Uh, consider consider e x x equal to y equal to e2, which is basically yeah. So this is uh, basically unit disk, uh, unit closed disk in complex plane. or you can write z belonging to C such that z equal to r I theta, r between 0 to 1, and there is no restriction over theta, and A equal to B equal to S1 equal to Z and to C such that Z equal to theta. You know, this is circle, unit circle in complete plane. This and F0 and F1 from E to S1 to E to S1 given by F0 okay, R exponential I theta equal to R exponential I theta and F1 R exponential I theta equal to R exponential I theta plus pi for every R exponential I theta in E2. So basically this is what this is the reflection of this is the F1 is reflection through origin, right? So if you consider the this E2 right, so if you take a point here, right, its image under F1 will be here, right? So if this is X, then this is F1X, and F0 is identity. So you can see that because F0 is identity, so obviously S1 goes to S1, it is fixed, S1 is fixed, and F1, if you have a point here, right, and on this S1, this is S1, then it will be mapped to a point here, right? So Y goes to F1. So you can see that F1 maps S1 to S1 itself. So F0 and F1, they are maps from here to here. So you know that they are maps. This F0, this is identity. So of course it is a map, and this is a map. Why this is of the form side, right? Z goes to some ZA for some A in C. So in our case, A we can consider exponential I pi, right? It's just a multiplication. So if you write Z equal to R exponential I theta, then ZA is nothing but R exponential I theta plus pi. So this kind of map Z going to ZA, where A is a fixed complex number, it is a continuous function. In uh, uh, It is a continuous function from C to C. So basically, uh, it maps E2 to E2 itself. Now, uh, here x prime you can consider 0, because f0 and f1 both are uh, they both agree at this. They both map this to this point to this point itself. So define uh, f from E2 S1 cross I to E2 S1 by f r I theta t. It is mapped to r exponential I theta plus t pi. Now, so this f, capital F, is uh, a continuous function from here to here. Again, this map you can consider composition of two maps. ZT goes to Z pi t. This, of course, it is a continuous map, continuous function. We should not. And then this goes to Z exponential I pi it pi. So uh, because this map which takes uh, yeah, so this is map which takes this to this is continuous. The map which takes this to this is continuous. So composition is continuous, and hence this is a continuous function. That is it is a map from here to here. Yes. So yeah. So F is a map, and that is a continuous function from here to here, and f r I theta 0 equal to uh, r theta equal to f naught theta, and f one pi is nothing but, and f I theta t equal to Yes. So this maps uh, uh, S1 T to S1 for every T. Uh, Sorry. So this maps uh, uh, is, yeah. So, so if you fix, so if you write R I theta into FT R theta, then this FT actually maps S1 to S1 for every T. So, uh, uh, yeah, hence uh, F is a homotopy from F0 to F1 relative to, because that 0 is fixed by uh, uh, F0, F1 and all the intermediate maps Ft. So what happens in this uh, homotopy actually is this. So it is, so when you increase t, right? So uh, f r exponential I theta comma t equal to r exponential I theta plus t pi, right? So here you can write that I t pi. So uh, each map, right? If you denote it by ft r exponential I theta, then each map ft is a rotation by an angle t pi, right? So it is rotate. This whole disk is rotated by an angle t pi. So each rotates, ft rotates the disk by an angle t pi. So for t equal to 0, that angle of rotation is 0. It means that there is it means that each point is fixed. For t equal to half, rotation is by pi by 2, right? For t equal to 1 upon 4, rotation is by pi by 4, right? And for t equal to pi, rotation is by pi. So it is like uh, uh, slowly and so you have f naught takes each point of E2 to E2 itself, uh, to that point itself, and then when you increase t, then each this ft rotates, uh, right? Basically, again, we should say that uh, these maps, right? Uh, there is a continuous deformation, right? There is a continuous deformation of F naught, right? To get F1. Slowly and slowly, F naught is getting deformed. Initially, it is identity, then it is a rotation by uh, 40 equal to maybe 1 upon 4. It is rotation by 1 upon 4. Then 40 equal to half, it is rotation by 1 upon pi by 2. Then 40 equal to 3 pi by 2, it is rotation by 3 pi by 4, part, and so on, right? So map is this map F naught is getting continuously deformed uh, to towards F1. Next, example 4. Uh, in example 4, we have uh, let x be an arbitrary uh, space and y be a convex subset of Rn. Let f naught f1 from x to y be maps uh, uh, which agree maps which agree on some subspace space x prime of x. Now define uh, capital F from x cross I to y by fxt equal to t f1 x plus 1 minus t f naught x. So again, this capital F is a map, that is a continuous function from here to here, because you can consider this map xt to t, then xt going to 1 minus t, right? Of course, f1 and f naught, they are already maps. So this is a map, just projection. This is also a map. This is from here to R, right? From x cross I to R, this map. So this also is from x cross I to R. So this is multiplied in this map is multiplied in this F1, and this one is multiplied in F naught. So this is this map T F1 x, that is x going to xt going to T F1 x. This is continuous function, that is a map, and xt going to 1 minus t f naught x. This is also a map. So their sum also will be a map. Uh, so this is a map, and fx0 is what you just see here. T equal to 0, this is 0, then this is f naught x, fx1 equal to f1 x. See, 1 minus 1 0, so this is f1 x, and xt equal to uh, t times equal to this f naught x equal to f1 x for every x belonging to x prime, because f naught and f1 x agree on x prime. So you have here f1 equal to f naught. So if you take f naught outside, then t plus 1 minus t will give you 1. Basically f naught x, which is equal to f1 x and x prime. So so hence f is f from capital F from f naught to f1 is a homotopy. F capital F is a homotopy from f naught to f1 relative to x prime. So how we have defined this homotopy, you just see here that if suppose we consider this to be y, which is convex, you can see, then uh, if f naught and suppose this is your x, x is anything. So suppose x goes to this is f1, right, and this is f naught. This is your f naught x. This is f1 x. Right now, here, what is this actually? This is this t f1 x plus 1 minus t f naught. This is the line segment when you allow t to vary in this interval 0 1. Then this denotes this gives this line segment joining f naught x and f1 x. So, but uh, and when you vary t, you will get different points. So for t equal to 0, you will have f naught x. For t equal to half, you have something, some point here. For t equal to maybe 3 upon 4, you will have some point here, right? And so on. So, but if y is not convex, then you will not be able to join f naught x and f1 x with the line segment which entirely lies in y, right? So what is a convex set? A convex set of convex subset of Rn is a set uh, uh, such that given any 2 points of that set, the line segment joining those 2 points entirely lie in that set, right? So because of that, we are able to define, because of convexity of y, we are able to define capital F like this. So yes, yeah. So this is a homotopy from f naught to f1 relative to x prime. So B stop here.